Hello, my name is Isabel, and today we'll be discussing Kronecker's Jugendtraum. Kronecker's Jugendtraum and the subsequent Hilbert's 12th problem, which extends upon the Jugendtraum, has led to the development of a lot of new research in this area of algebraic number theory, and there's a lot of rather advanced in this area of research, and so this talk will give an overview of the problem as well as the major steps that have led to the development of the field in which this problem now lies in. It's mathematics that we have not talked about in class. And so first, to discuss this problem, let's start with some intuition. So in class, we've mentioned this problem when we mentioned this problem very briefly when we discussed the solvability of polynomials over the rationals. And not every polynomial is solvable by radicals. And so we then wonder, okay, so how do we then describe and generate the roots to these polynomials and the splitting fields in which they live? And one example that we saw was we can describe the roots of unity with complex exponentials. And so here we found a function that can output roots of polynomials at certain values of this function. And we'll be making an analogy back to this exponential function when we talk about other functions that might be harder to understand. And so to understand Kronecker's Jugendtraum, keep in mind a couple things. The question we're asking is, how can we describe finite abelian field extensions, and what functions output roots of polynomials at special values of this function? And so Kronecker's Jugendtraum was named after the mention of the problem in an 1880 letter that Kronecker wrote to Dedekind. And the original text is first, and because we all speak German, I've put the English translation below that. The English translation is still a little bit hard to understand as it's describing concepts in a different way than we've been talking about them in class, and so we'll break down the statement a little bit. So what Kronecker is writing here is really a comparison. So in red, he's saying, okay, I want to show this, as we've already shown the stuff in blue. And so we'll get into what the red statement is and what the blue statement is next. So first, we're going to start with what he's already proved, which is the Kronecker-Weber theorem. And he actually didn't prove it. He originally stated the theorem in the 1850s, but it was incorrectly proved several times by him and then later Weber before Hilbert first did the first complete proof in 1896. And so here is the Kronecker-Weber theorem, which it states every finite abelian extension of the rational numbers Q is a subfield of a cyclotomic field. So if K over Q is a finite abelian extension, then K is a subfield of Q extended by a root of unity. And so if you recall that we can write the roots of unity as special values of a function, then we have this on the bottom here. And so again, keep in mind this analogy to the function of a complex exponential. We can write roots as outputs of this function. And so now we move on to describing the red part of the phrase, where Kronecker is describing what he wants to be true. And so what he's saying is that I imagine that we can generalize the Kronecker-Weber theorem to imaginary quadratic fields instead of just being over Q. Kronecker was basing his prediction off of earlier work that was done by Abel, where he showed that some extensions of Q extended by I could be created with special values of the Levenstatic elliptic function. And so you can basically think of this function as if we put in special values of tau, then we'll get roots of polynomials in Qi. Just as we put in special values into the complex exponential function and got out roots of polynomials in Q. And so Kronecker is taking Abel's work and he's imagining that it generalizes to other imaginary quadratic number fields, not just Q extended by I. Kronecker then imagines that the function that can describe all these extensions of imaginary quadratic number fields will be an elliptic function with singular moduli. For the purposes of this talk, we won't get too much into exactly what that function is, but these functions essentially yield geometric interpretations, which were being thought of by mathematicians at the time. And Actually, it was shown about 20 years later that this is actually true. And most of the work that was done in showing this theorem came from the work of a Japanese student of Hilberts, Takaki, and it was in his doctoral thesis in 1903. Takaki showed exactly what had constructed, but it showed that his construction holds in general. So for any finite abelian extension of Qi, it can be constructed by appending a particular value of the Lemniscate elliptic function. Today, we then have the following theorem. So for any imaginary quadratic field K, any finite abelian extension of this field, L will be a subfield of K adjoined with J of T. J is the J function. Again, think about this just as if J was the complex exponential function and tau was a particular value that we put into this function to output a root of a polynomial. And so the example that's shown on the bottom of this slide here of an actual field extension that was built off of an imaginary quadratic fields. And because we don't really have insight into what the J function is, this example might not necessarily be the most illustrative, but the key takeaway from this example is that the outputs of J are roots of polynomials in imaginary quadratic number fields. And so if we append them onto the base quadratic number fields, then we will get the field extension that contains all the roots of that polynomial. And just for a little bit of insight into what the J function is, we do see that the J function is an elliptical modular function, just as Kronecker expected. But from the definition that we see on the right here, and this definition is taken from Wolfram, and we can see that it's not a simple definition by any means, and so we won't spend too much time on discussing what this actually is. Again, think of the utility of this J function as it is able to generate the roots of polynomials given special values of tau. And so now let's move back into the big picture and discuss Hilbert's 12th problem. And so when Hilbert was posing his problem, he took Kronecker's Jugendtraum and he extended it to, instead of just being about quadratic number fields, he extended it to ask, how can we generate the abelian extensions to any number field, not just quadratic number fields? And generally, the problem is still open, as mathematicians have only found the solutions to very select cases of number fields, such as imaginary quadratic fields, as we mentioned earlier. And we've also found that there are counterexamples to extensions of other base fields that cannot be generated by the J function, and so this means that it's not true that the J function will be able to describe every finite abelian extension to any number field out there. And so the answers to Hilbert's 12th problem lie in functions that have yet to be identified. And so research into the Jugendtraum and Hilbert's 12th problem continues on to today. And research in this area lies in what is now known as class field theory. And so class field theory can be summarized as the study of abelian field extensions. And class field theory was extensively developed by Takaki at the forefront. And so Hilbert had posed his 24 problems as predictions for what mathematicians would, one, find important, and two, want to focus on in the 20th century. And so this was one of the problems that Hilbert was really correct about predicting, that it would drive the future of mathematics, as throughout the 20th century there were a lot of developments in this area, and even today, more than a century later, there's still a lot of research going into this area.